Heat capacity or thermal capacity is a measurable physical quantity equal to the ratio of the heat added to an object to the resulting temperature change. The SI unit of heat capacity is joule per Kelvin and the dimensional form is L2mt-2θ-1. Specific heat is the amount of heat needed to raise the temperature of a certain mass by 1 degree Celsius. Heat capacity is an extensive property of matter, meaning it is proportional to the size of the system. When expressing the same phenomenon as an intensive property, the heat capacity is divided by the amount of substance, mass, or volume, so that the quantity is independent of the size or extent of the sample. The molar heat capacity is the heat capacity per unit amount of a pure substance, and the specific heat capacity, often simply called specific heat, is the heat capacity per unit mass of a material. Occasionally, in engineering contexts, the volumetric heat capacity is used. Temperature reflects the average randomized kinetic energy of constituent particles of matter relative to the center of mass of the system, while heat is the transfer of energy across a system boundary into the body other than by work or matter transfer. Translation, rotation, and vibration of atoms represent the degrees of freedom of motion which classically contribute to the heat capacity of gases, while only vibrations are needed to describe the heat capacities of most solids, as shown by the Dulong-Petit law. For quantum mechanical reasons, at any given temperature, some of these degrees of freedom may be unavailable, or only partially available, to store thermal energy. In such cases, the specific heat capacity is a fraction of the maximum. As the temperature approaches absolute zero, the specific heat capacity of a system approaches zero, due to loss of available degrees of freedom. Quantum theory can be used to quantitatively predict the specific heat capacity of simple systems. History. In a previous theory of heat common in the early modern period, heat was thought to be a measurement of an invisible fluid, known as the caloric. Bodies were capable of holding a certain amount of this fluid, hence the term heat capacity. Named and first investigated by Scottish chemist Joseph Black in the 1750s. Since the development of thermodynamics during the 18th and 19th centuries, scientists have abandoned the idea of a physical caloric, and instead understand heat as changes in a system's internal energy. That is, heat is no longer considered a fluid, rather, heat is a transfer of disordered energy. Nevertheless, at least in English, the term heat capacity survives. In some other languages, the term thermal capacity is preferred, and it is also sometimes used in English. Units. Extensive properties in the International System of Units. Heat capacity has the unit joules per Kelvin. An object's heat capacity is defined as the ratio of the amount of heat energy transferred to an object and the resulting increase in temperature of the object, assuming that the temperature range is sufficiently small so that the heat capacity is constant. More generally, because heat capacity does depend upon temperature, it should be written as where the symbol delta is used to imply that heat is a path function. Heat capacity is an extensive property, meaning it depends on the extent or size of the physical system in question. A sample containing twice the amount of substance as another sample requires the transfer of twice the amount of heat. Intensive properties. For many experimental and theoretical purposes, it is more convenient to report heat capacity as an intensive property than intrinsic characteristic of a particular substance. This is most often accomplished by expressing the property in relation to a unit of mass. In science and engineering, such properties are often prefixed with the term specific. International standards now recommend that specific heat capacity always refer to division by mass. The units for the specific heat capacity are, in chemistry, heat capacity is often specified relative to 1 mole, the unit of amount of substance, and is called the molar heat capacity. It has the unit. For some considerations, it is useful to specify the volume-specific heat capacity, commonly called volumetric heat capacity. which is the heat capacity per unit volume and has SI units. This is used almost exclusively for liquids and solids, since for gases it may be confused with specific heat capacity at constant volume. Alternative unit systems. While SI units are the most widely used, some countries and industries also use other systems of measurement. One older unit of heat is the kilogram-calorie. Originally defined as the energy required to raise the temperature of 1 kilogram of water by 1 degree Celsius, typically from 14.5 to 15.5 degrees Celsius. The specific average heat capacity of water on this scale would therefore be exactly 1 cal. However, due to the temperature dependence of the specific heat, a large number of different definitions of the calorie came into being. Whilst once it was very prevalent, especially its smaller CGS variant, the gram-calorie, defined so that the specific heat of water would be 1 cal. In most fields the use of the calorie is now archaic. In the United States, other units of measure for heat capacity may be quoted in disciplines such as construction, civil engineering, and chemical engineering. A still common system is the English engineering units, in which the mass reference is pound mass and the temperature is specified in degrees Fahrenheit or Rankine. On this scale, the specific heat of water would be 1 pound cal. More common is the British thermal unit, the standard unit of heat in the U.S. construction industry. This is defined such that the specific heat of water is 1 BTU. Measurement of heat capacity. It may appear that the way to measure heat capacity is to add a known amount of heat to an object, and measure the change in temperature. This works reasonably well for many solids. However, for precise measurements, and especially for gases, other aspects of measurement become critical. The heat capacity can be affected by many of the state variables that describe the thermodynamic system under study. These include the starting and ending temperature, as well as the pressure and the volume of the system before and after heat is added. So rather than a single way to measure heat capacity, there are actually several slightly different measurements of heat capacity. The most commonly used methods for measurement are to hold the object either at constant pressure or at constant volume. Gases and liquids are typically also measured at constant volume. Measurements under constant pressure produce larger values than those at constant volume because the constant pressure values also include heat energy that is used to do work to expand the substance against the constant pressure as its temperature increases. This difference is particularly notable in gases where values under constant pressure are typically 30% to 66.7% greater than those at constant volume. Hence the heat capacity ratio of gases is typically between 1.3 and 1.67. The specific heat capacities of substances comprising molecules are not fixed constants and vary somewhat depending on temperature. Accordingly, the temperature at which the measurement is made is usually also specified. Examples of two common ways to cite the specific heat of a substance are as follows. Water. Cp equals 4185.5 J. Water. CVH equals 74.539 J. For liquids and gases, it is important to know the pressure to which given heat capacity data refer. Most published data are given for standard pressure. However, quite different standard conditions for temperature and pressure have been defined by different organizations. The International Union of Pure and Applied Chemistry changed its recommendation from 1 atmosphere to the round value 100 kilopascals. Calculation from first principles. The path integral Monte Carlo method is a numerical approach for determining the values of heat capacity, based on quantum dynamical principles. However, good approximations can be made for gases in many states using simpler methods outlined below. For many solids composed of relatively heavy atoms, at non-cryogenic temperatures, the heat capacity at room temperature approaches 3R equals 24.94 joules per Kelvin per mole of atoms. Low-temperature approximations for both gases and solids at temperatures less than their characteristic Einstein temperatures or Debye temperatures can be made by the methods of Einstein and Debye discussed below. Thermodynamic relations and definition of heat capacity. The internal energy of a closed system changes either by adding heat to the system or by the system performing work. Written mathematically, we have or for work as a result of an increase of the system volume. We may write, if the heat is added at constant volume, then the second term of this relation vanishes and one readily obtains. This defines the heat capacity at constant volume, CV, which is also related to changes in internal energy. Another useful quantity is the heat capacity at constant pressure, Cp. This quantity refers to the change in the enthalpy of the system, which is given by a small change in the enthalpy can be expressed as and therefore. At constant pressure, we have these two equations, are property relations and are therefore independent of the type of process. In other words, they are valid for any substance going through any process. Both the internal energy and enthalpy of a substance can change with the transfer of energy in many forms, i.e., heat. Relation between heat capacities. Measuring the heat capacity, sometimes referred to as specific heat, at constant volume can be prohibitively difficult for liquids and solids. That is, small temperature changes typically require large pressures to maintain a liquid or solid at constant volume, implying the containing vessel must be nearly rigid or at least very strong. Instead, it is easier to measure the heat capacity at constant pressure and solve for the heat capacity at constant volume using mathematical relationships derived from the basic thermodynamic laws. Starting from the fundamental thermodynamic relation, one can show where the partial derivatives are taken at constant volume and constant number of particles, and constant pressure and constant number of particles, respectively. This can also be rewritten where is the coefficient to thermal expansion, is the isothermal compressibility. The heat capacity ratio or adiabatic index is the ratio of the heat capacity at constant pressure to heat capacity at constant volume. It is sometimes also known as the isentropic expansion factor. Ideal gas. For an ideal gas, evaluating the partial derivatives above according to the equation of state where R is the gas constant for an ideal gas, substituting this equation reduces simply to Mayer's relation. Specific heat capacity. The specific heat capacity of a material on a per mass basis is which in the absence of phase transitions is equivalent to, whereas the heat capacity of a body made of the material in question is the mass of the body, is the volume of the body, and is the density of the material. For gases, and also for other materials under high pressures, there is need to distinguish between different boundary conditions for the processes under consideration. Typical processes for which a heat capacity may be defined include isobaric or isochoric processes. The corresponding specific heat capacities are expressed as from the results of the previous section. Dividing through by the mass gives the relation a related parameter to is, the volumetric heat capacity. In engineering practice, for solids or liquids often signifies a volumetric heat capacity, rather than a constant volume one. In such cases, the mass-specific heat capacity is often explicitly written with the subscript, as, of course, from the above relationships. For solids, one writes for pure homogeneous chemical compounds with established molecular or molar mass or a molar quantity as established. Heat capacity as an intensive property can be expressed on a per mole basis instead of a per mass basis by the following equations analogous to the per mass equations. Equals molar heat capacity at constant pressure equals molar heat capacity at constant volume, where N is the number of moles in the body or thermodynamic system. One may refer to such a per mole quantity as molar heat capacity to distinguish it from specific heat capacity on a per mass basis. Polytropic heat capacity. The polytropic heat capacity is calculated at processes if all the thermodynamic properties change equals molar heat capacity at polytropic process. The most important polytropic processes run between the adiabatic and the isotherm functions. The polytropic index is between 1 and the adiabatic exponent. Dimensionless heat capacity. The dimensionless heat capacity of a material is where C is the heat capacity of a body made of the material in question. N is the amount of substance in the body, R is the gas constant, N is the number of molecules in the body. K is Boltzmann's constant. In the ideal gas article, dimensionless heat capacity is expressed as and is related there directly to half the number of degrees of freedom per particle. This holds true for quadratic degrees of freedom, a consequence of the equipartition theorem. More generally, the dimensionless heat capacity relates the logarithmic increase in temperature to the increase in the dimensionless entropy per particle, measured in nats. Alternatively, using base 2 logarithms, C** relates the base 2 logarithmic increase in temperature to the increase in the dimensionless entropy measured in bits. Heat capacity at absolute zero. From the definition of entropy, the absolute entropy can be calculated by integrating from 0 kelvin's temperature to the final temperature Tf. The heat capacity must be 0 at 0 temperature in order for the above integral not to yield an infinite absolute entropy, which would violate the third law of thermodynamics. One of the strengths of the Debye model is that it predicts the proper mathematical form of the approach of heat capacity towards zero, as absolute zero temperature is approached. Negative heat capacity. Most physical systems exhibit a positive heat capacity. However, even though it can seem paradoxical at first, there are some systems for which the heat capacity is negative. These are inhomogeneous systems which do not meet the strict definition of thermodynamic equilibrium. They include gravitating objects such as stars, galaxies, and also sometimes some nanoscale clusters of a few tens of atoms, close to a phase transition. A negative heat capacity can result in a negative temperature. According to the virial theorem, for a self-gravitating body like a star or an interstellar gas cloud, the average potential energy UPOT and the average kinetic energy UKIN are locked together in the relation the total energy U therefore obeys if the system loses energy. For example, by radiating energy away into space, the average kinetic energy actually increases. If a temperature is defined by the average kinetic energy, then the system therefore can be said to have a negative heat capacity. A more extreme version of this occurs with black holes. According to black hole thermodynamics, the more mass and energy a black hole absorbs, the colder it becomes. In contrast, if it is a net emitter of energy through Hawking radiation, it will become hotter and hotter until it boils away.